G'day viewers. In this segment I'll talk about TCP slow start. So recall that we're trying to get TCP to implement an AIMD control law because this will give us a good allocation that's efficient and fair. Slow start is one of the mechanisms that TCP uses as part of its additive increase mechanism. So here's just a little more background context before we go into the details. I've said that TCP is trying to get to an AIMD control law. The way we're going to use it implement it in TCP is to have the sender implement a congestion window and adjust the size of the congestion window. This controls the rate indirectly. The rate we'll get is the congestion window divided by the round trip time. We're also going to use feedback from the network in terms of packet loss to understand when there's congestion. And our problem of using AIMD to adjust the size of the congestion window is really difficult for TCP because we want TCP to be a solution that works across a very wide range of RTTs and rates for links in the network. So it's going to be difficult just to pick a number and have it go to any of those rates or any kind of constants. We have to be a little careful about. The problem in implementing additive increase directly with the congestion window, which slow start will solve, is this. We want to fairly quickly get the size of the congestion window to be somewhere near the ideal congestion window, which will give us the right rate. If we're hovering anywhere near there and oscillating back and forth, that's where AIMD ends up, then we have a good bandwidth allocation. But that ideal can vary greatly depending on the RTT and the rate of link. So we really don't know a priori what it should be. If we took a guess, we could easily be way too small or way too large. Any fixed size sliding window is going to be problematic because not only will it be either way too small or way too large, but it's also very rough on the network. It just injects a burst which can lead to queuing and packet loss. The whole reason for using a congestion window in small bursts is that we're nice and smooth on the network. So we can use our congestion window with additive increase using small bursts to additively change the congestion window, make it bigger and bigger and bigger. In this way, we'll have smooth traffic running with the ACT clock that we're seeing at about the right congestion window, eventually when additive increase increases the congestion window to where we want to. But it might take a very long time to get anywhere near C-wind ideal and become efficient. And that's because the network could simply be one for which this is large compared to a step size we'll have to conservatively choose. Slow start is the solution to this problem. Slow start doubles C-wind every round trip time. So it's adapted to the round trip time already because we can measure that. By doubling the congestion window, we have exponential growth here. So 1, 2, 4, 8, 16. The growth is initially fairly slow, but rapidly becomes very large. That's what exponentials do. So this means that it will reach large values very quickly in a small amount of time, but it will initially start off more softly. So it will tend not to overshoot so much. We can see here slow start compared, and that's this exponential curve. Oops. Maybe not very good drawing there, to two alternatives. So slow start will reach up to this ideal level here much more quickly than additive increase, which will take a very, very long time to get to this ideal value. And on the other hand, slow start is going to reach there fairly quickly, not as fast as the fixed allocation, but on the other hand, it's adapted traffic smoothly to the network. So we'll avoid a lot of enormous bursts of traffic. So slow start is a pretty good compromise between these two things. You'll note, by the way, that it's not very slow in how it increases the size of the sliding window. It's only slow by comparison of jumping from 0 to the maximum window size in one step. But we're not quite done. So slow start can exponentially increase the window size to get to about the right neighborhood. But eventually, packet loss is going to occur. At some stage, the window will be too large, we'll be sending too much traffic into the network, the queues will build, packets will lost, and the network will be congested. When that happens, we'll get a timeout because we're lacking an acknowledgement. We'll know that a packet's been lost. Now at this stage it's too late. We're already congested, and in fact the loss happened quite a while ago. It just took us a little while to find out. So that means that C-win is too large. What we'll do instead, next time that we begin to increase the congestion window from the beginning and ramp up, is that we'll switch away from our doubling solution, our slow start, to additive increase, which we wanted all along when we're in the vicinity. So this way we'll additively increase and more slowly adapt the congestion window somewhere around the right value. Now, in terms of how TCP adapts the congestion window, it works something like this. You expect a loss when the congestion window is about twice the bandwidth delay product, because that's how much information can fit in the network. Plus there's a queue size. We could also store some packets in the queue. So we will create this new variable, SS_thresh, slow start threshold, and we'll set that to be half of the size of the congestion window when you detect loss. Because when you detected loss, we'd already gone too far. By setting it to half, we're sort of being a little more conservative. And here's the combined solution you get, which is what we use instead of additive increase to quickly get the congestion window to about the right place and then additively increase for the last part of the segment. You can see here that we slow start until we reach the slow start threshold, and then we're going to additively increase. And we'll spend most of our time in the additive increase phase, not in the slow start phase. And you'll note that the ideal is here. We'll probably additively increase past that until eventually we cause loss somewhere up here with a higher congestion window. And at that time, we'll get some timeout and we'll know that we've gone too far. I can show you some timeline graphs just to get the hang of how slow start works, to double and followed by additive increase. Here's what slow start looks like on a timeline. So we have the sender on the left and the receiver on the right. Here is a data packet being sent, and here is an ACK coming back. We want to double the congestion window every round trip time. Well, a neat way to do that is to increment the congestion window by 1 packet every time you get an ACK. In this way, every 1 packet in a window becomes 2 packets in the next window. So this is why we're doubling. So when we get this ACK here, we could double our congestion window from 1 to 2, and, add 1 to the congestion window, add 1 packet to the congestion window. That will let us send 2 packets, because we added 1 to the congestion window, and we also got another packet ACK, so that lets us send 2 new packets. Each of those will cause ACKs to be returned, and you can see here, every time we receive an ACK, we send 2 packets. 1 for the new one that we can send because an ACK arrived, so the sliding window could advance, and 1 for increasing the congestion window. And you can see here on the right hand side, if I divide the time into round trip times, we have 1, 2, 4 packets going there into the network. After that, we've reached the twice the bandwidth delay product and the pipe is full, so any other packets would have to be stored in router queues or somewhere else, and eventually they would cause loss. And now, for a contrast, let's look at how additive increase is implemented with packets. Here we're starting from 1. You would normally slow start somewhere, but for the sake of a simpler example, we'll slow start from 1. So with additive increase, we would like to add 1 packet to the congestion window every round trip time. So here's a round trip time. On the right, I'm just dividing time as before, and you can see we're still sending packets and getting ACKs back as before. The first time we get an ACK, a round trip time has gone by, so we add 1 to the congestion window, and we get to send 2 packets. The next time, though, you can see that we're only sending 2 packets in response to the last ACK there, right? And that's what's allowing our that's what's allowing the congestion window. That's where the congestion window is growing, and the reason why we're adding 1 packet to the congestion window over time. Now, just in the same way we added 1 packet every C-wind to double, there's also a heuristic for adding 1 packet to the congestion window every C-wind. Sorry, before I meant if you add 1 packet every time you get an ACK, you will double the congestion window every RTT. Now we only want to add one packet to the congestion window every RTT. Well, in an RTT, you should get ACKs for about C-wind packets, because there are C-wind packets every round trip time. So if you just add, one on C-wind, fraction of a packet, to the congestion window every time you get an ACK, you'll end up in about the same place. I'm skipping a little bit ahead to the implementation, so let me just move to that and tell you. What I would like you to take away from this diagram is simply that every round trip time, the congestion window is going up by one packet. So for most of the packets, the ACK simply triggers another packet, but occasionally we're sending two. That's a small burst, which the network will smooth out. TCP Tahoe implements slow start followed by additive increase. And it does this using the slow start and additive increase rules as follows. For slow start, we start with a congestion window of 1, or you could start with some other small initial value. Modern implementations have recently, to get things going quickly, started using 4 or even 10 packets as an initial congestion window. And you add one packet to the congestion window every time you get an ACK. So we're doubling the congestion window over time. For additive increase, once you pass the slow start threshold, we'll get to that in a minute, you also increase the congestion window over time. But you don't do it so quickly. We want to add one packet to the congestion window every round trip time, but we don't want to keep a separate round trip time timer. So instead, what we do is we add one on C-wind packets, that fraction. We can do this because congestion window is measured in bytes, so you can have, 4.25 packets. That's a congestion window that big. We add this fraction to the congestion window every time we get an ACK. And since there are about C-wind packets every round trip time, we're adding approximately one packet every round trip time by using this heuristic. It's not exact if you do the math, and that just doesn't matter. Now we have the rules for these two phases. We have to work out how they relate. Well, remember we use this switching threshold, SS thresh. Initially you can set it to infinity, so you just slow start until you cause loss. In the future, when there's a reasonable value of SS thresh, when the congestion window reaches this threshold, we change from slow start, where you double, to additive increase. When you get a loss, you set slow start threshold to be half of the congestion window that caused the loss. So the first time, eventually we'll slow start until we cause loss. We'll remember where that congestion window was, set slow start threshold to be half of that. Now, in the future iterations, we'll be able to slow start up to about the right value and then slowly additively increase to spend most of our time at a reasonable congestion window that's sending traffic at a reasonable rate into the network. And finally, another rule here is that after you've timed out, you go back and you slow start from all the way from a congestion window of 1 or your other small value. That's one thing you may wonder about, actually. The misfortune of timing out and starting again with slow start. After all, we wanted to implement additive increase, multiplicative decrease. We're doing the additive increase bit, but you would think after loss we should simply multiplicatively decrease the congestion window and keep going. That is where we want to get to. The problem here is that we detect loss with timeouts. Now when you do that, timeouts, because they have to be conservative, are usually sufficiently long that all of the packets that have gone into the network have been ACKed already. We've received whatever ACKs there are, and in fact our ACK clock has now run down. So we no longer have any nice clock which will help us send packets into the network at a nice, smooth, gradual rate that won't cause queues to build up. If we simply kept a big congestion window and started, we would send an enormous burst of traffic into the network potentially and cause a lot of loss. Instead, if we use slow start, that's a way to start from nothing when the network's gone quiescent and to ramp up our ACK clock and our congestion window fairly quickly to about the right value. So if we're going to fix this and really get to AIMD, then we need some way to detect loss before a timeout. And this is what we'll see next with other TCP heuristics that are used in TCP Reno.